I wanted to make a short video to help with the understanding of lesson 5.2. And I always think things are easier to understand if we work through an example and apply it in some sort of daily life kind of thing. So let's start this with a small question here that I have some data to support. And the question is, does the high temperature of the day affect hot coffee sales? So we're going to suppose we are a small business owner and we're curious about this relationship between the high temperature of the day and how much they're going to make in those coffee sales. So this data that we have here is for 15 randomly selected days from a coffee shop, and it's their daily sales in hot coffee and the high temperature that was achieved that day. So I'm not great at just looking at two columns of data and understanding exactly what's going on. I need tools to help me understand how they relate to one another, how they're associated. So a scatter plot is a great way to do that. So here's a scatter plot of the data. And once we get it there and we have 15 dots that correspond to the 15 days, we can see that there might be something to the temperature outside with this type of product they sell. And you can see there's this upper left here and down to the lower right. You can see this trajectory as my mouse is sort of tracing over this. And it appears that as temperatures are going up, their coffee sales are decreasing. So this is a great way to visualize it. It would be helpful for the business owner to know this, but we could go a step further with this. So, the whole point of statistics is to summarize, take a lot of information and summarize it into something that's easy to understand. So there's one thing we can do with this, since it looks like it has this sort of straight line trajectory that decreases as the temperature gets higher, then why not put the least squares regression line, or as you might have heard it called in another class, the line of best fit with the data. And so this line is now further summarizing the relationship between high temperature and sales. And, the lines are pretty easy to understand. Most people understand lines from their algebra classes. So it's a nice way. If the data merits and has this shape, then we're going to summarize the data and then use the line to learn more about this relationship. So the equation of this line, I drew it there, or I should say the computer drew it for me. But the equation of this line is this sort of brownish line is sales equals 3559.94 minus 32.17 times temp. So that's our linear equation, and that describes the slope right here of the line, and of course the height of the line here, how high up or down it is. So let me give you an idea of how this was determined, because sometimes it just seems like it's magic. Oh, wow, there's this line that, okay, I believe you, it fits. So the algorithm that the computer is going through, or software packages are going through, are based off sound mathematics. And I want to kind of explain that to you in just a really kind of no nonsense manner. So hang with me. I'm going to show this plot one more time. So here is our hot coffee sale. Same plot. I just have it on a slightly different software package because I could do more with some effects here. Here is the hot coffee sales and high temp again. And I want you to just bear with me. I know there's a lot of numbers over here to the right, but here's the original data again, high temp and hot coffee sales. And so just for a moment, so we can get our bearings and I can kind of explain to you what's going on, I want to focus in on a day where it is 39 degrees as the high temperature right here, the first 39 in the list. So on that day, they saw $2,480 in sales. Now, I want to show you how this column predicted came about. So let's look under the graph. There's our equation that we talked about earlier, the line of best fit. And what I'm going to do to predict the sales on that day, I'm going to use the least squared regression line, or the line of best fit. So I'm going to accomplish that by plugging 39 in place of temperature into my equation. Now, if you take a moment and you do the arithmetic there, make sure you multiply the two values that are in the 30s together, and then take that product and subtract it from 3559, you would see that the model, the linear model, would predict the sales that day to be $2,305.31. So that's where this predicted comes from. That's what the model would predict. This right here, 2480 for this particular day, is what we observed in sales, but the model would have predicted it a little bit lower. Now, what you might wonder is, what is the other two columns? Well, hold on. I want to keep focusing in on that 39 degrees. So we're going to create something that's called error. Clearly, this pink line here can't touch all the dots. It's trying to get as close as possible to all of them simultaneously, which is a hard thing to do. So it's figured out the best way to do that, where we can minimize the distance from the dot to the linear model. And so I just have these little dashed lines here to sort of accentuate the distances, or what I'm going to call error. So you can see in some cases, there's right down here, if you can see my mouse, there's a big error there. And in other cases, if I look to the left, there's a small error, small distance there. So let's focus again in on this first day with 39 degrees. And if I take the observed, the 2,480, and subtract off what the linear model would have predicted, which is the 2305.31, you can see it was off by about $174.69. And that is the error. That's what the model is trying to minimize. It's trying to minimize the error produced by the model, which is also the distance the dots are from the pink line here. Now, this was done for all 15 days in this table, which is what makes it look a little crazy. Now, if you notice, there was another day where there was 39 degrees in our random selection right underneath, and it is incredibly close to the actual model. And you can see there's on that day, it was $22,280 they made. Same predictive value because it's the same model. And you can see the error is just about $25, much different because it's a lot closer to the model. Now, we want to minimize error. We want to minimize the distances. So what I would like to do, if it were simple, would just be add up all the errors and see collectively how much error we're producing with this linear model. Well, when you add them all up, unfortunately, the negatives and positives will play off each other and cancel each other out and bring you down to a number that's really close to zero. And that's not helpful because we know there's error here. So we're going to do what we did that was similar with the standard deviation when we had the same problem, which is to square the error, which in squaring the number, we still sort of keep the magnitude of it, but we don't have to deal with the negative and positive, because when you multiply a negative number by a negative number, you're going to get a positive number. So hang with me here. We're going to add up all these. So if you square 174.69, you get 30,448.07. If I square this much smaller number here for the other 39 degrees, you can see that squared error is smaller. So the algorithm adds up all these squared errors and comes up with an overall sum, just a total of all of them added up. And this represents how well the model fits the data. So I know you're like, what? It's about 500,000 there. And that's fine. The data we're working with has numbers that are quite large. And that's when we call something the least squares regression line, it's because there's adding up all the squared errors and trying to find the total that's the least. I want to take just a minute to show you one more slide of a model that, if you can see me going back, clearly doesn't fit the data as well. This one here, this sort of brownish golden model here. And the equation for that is, this is, again, not the line of best fit, but just another proposed model, is here. Now, if I go through this whole process, I'm not going to speak it out loud, and do the predicted value for every single one of the 15 dots using this model with a lot more distance here, as you can see, a lot more dotted line, square my errors and add them up, you can see that it adds up to a total that's much larger than 500,000. It's over 1,000,000. So essentially, the line of best fit minimizes the squared error or the squared distances. So that's how it comes about. Now, that's how it works. I'd like to take you through, in the next video, just a quick review of how do we get this line. This one back here, this line of best fit right down here at the bottom. That was something that was provided to me through using statistical software. In the next video, I'll show you how to do that.